So now that I've introduced you to the fork join pool, let's start talking about its structure and functionality. And you'll see this is a multi-part lesson because there's a lot of things to talk about. And in particular, we're going to talk about the fork join pool itself and how it's structured, as well as the tasks that it executes in the fork join pool. So the fork join pool itself is an implementation of some other interface called the executor service interface. And we won't talk a lot about the executor service in this class. The executor service is something we'll cover in a lot more detail in the spring class. The executor service is the basis for a bunch of subclasses that form the so-called Java executor framework. And the Java executor framework is a set of interfaces and classes that provide different thread pool implementations, starting with Java 5, which came out about the 2004 timeframe or so. So you can see here we've got the executor interface, which is very simple, executor service, which has a whole bunch more stuff. Then there's this thing called the abstract executor service. That's a class that implements the interface. And then we've got thread pool executor, which is an extension of the abstract executor service, and fork join pool, which is an extension of the abstract executor service. And there's even more stuff that we're not going to go over here, but just to give you a sort of a feel for how things are laid out in general. There are these other implementations of the executor service are used to execute implementations of common interfaces called runnables and callables. Runnable is a very, very simple interface. It has a single method called run. This is basically the command pattern or the command processor pattern. And then the callable is an interface that has a call method that returns a value. Run does not take any parameters and returns no value. Call does not take any parameters and returns a value. And you can use callable for various things like the active object pattern and so on. We're not going to talk much about this stuff at all. Instead, we're going to focus on what the fork join pool does. And what the fork join pool does is it executes so-called fork join tasks. And fork join tasks, as you'll see, have the ability to be forked and joined. And so that's really the workhorse of this whole thing. It's also possible for the fork join pool to execute runnables and callables, just like other implementations of the executor service interface. However, that's not its main purpose. If you use the fork join pool to execute callables and runnables, you're really missing the point of what it's able to do, because it's able to do a lot more than that. So that obviously raises the question, what is a fork join task? So a fork join task is a class that is going to associate a chunk of data, a subset of the overall data, along with some computation on that data. So that's basically what it is. It's a class that connects data with computation. And the whole purpose of this thing is to support so-called fine-grained data parallelism. And you can read more about that here. But the basic idea is you can have lots and lots and lots of fork join tasks, and they're going to be sort of multiplexed over a smaller number of normal Java threads. And this is the visualization of this that I always get a kick out of. So a fork join task is a little scrawny, lightweight, computational object, and in contrast to the Java thread, which is what makes up the pool of worker threads. Java threads have a lot more stuff going on. They have their own runtime stack, they have their own registers, they have their own thread-specific storage, and so on. Whereas in contrast, the fork join pool has very little. But one of the nice things about that is you can actually have hundreds or thousands or tens of thousands or hundreds of thousands of fork join tasks, because they're all real scrawny and meager, and they can then be run and multiplexed in a much larger pool of worker threads. I'm sorry, you have a much larger number of fork join tasks that can run in a much smaller pool of worker threads. So you can have a pool of worker threads that has, as many threads as there are cores, or roughly the same number of threads as there are cores on the computer. And then you can have lots and lots and lots and lots of these lightweight fork join tasks that are running on top. And the key theme here is multiplex, right? So we're going to have lots of these things running on a smaller number of worker threads. And it'll come as no surprise that all these fork join tasks, when they're not running, will be sitting around in queues waiting to be picked up and processed by a worker thread in the pool of worker threads. Each worker thread has its own stack, its own registers, its own thread-specific storage, and so on and so forth. So those things are actually fully fledged, muscular elements of computation, units of computation. Now, the ForkJoinTask class has two methods that are used to control parallel processing to get things to run and merging of the results. And they are fork and join, surprise, surprise. And this discussion will kind of help illustrate at a high level what fork and join do. And we're going to take a crack at this from different perspectives because it takes a little while to get your head around what's going on because there's a lot of subtlety happening under the hood that's somewhat implicit here that doesn't reach out and grab you right at first glance when you just look at the APIs. So fork, when you call fork on a fork join task, that arranges to asynchronously execute this task in the appropriate fork join pool, which could be the common fork join pool, which could be some user-specific fork join pool, but it basically says, queue this guy up to run. So you can think of fork as kind of like a really lightweight version of thread.start. When you say thread.start, that creates a thread, which is much heavier weight, of course, gives it a runtime stack, starts executing the entry point method, and so on and so forth. So fork is a little bit like that, except that it doesn't start to execute right away. It just arranges to execute it. And what it does is it sticks, when you call fork, it will place the task or subtask that you forked onto the work queue for the worker thread in the fork join pool in the context of which fork was called. So whenever something takes place in the fork join pool, it's in the context of a fork join thread, and so a real thread, not a fork join task. And so as a result, it'll stick that on its internal work queue. It's all done implicitly and magically for you. So that's fork, right? So we fork, and when we fork, we end up forking what are called child tasks. So you have children, you fork, you get a child, and that child is put on the queue. Then join is used to return the result of the computation when it's done. And of course, as we said before, there's a couple different variants of join. Sometimes you return a real result, sometimes you just know that something is finished. Now, here's the really tricky part, and this is so weird. Remember we talked before briefly about thread join. So thread join is a method that's defined on thread, and when you join a thread, it blocks the calling thread until the thread you're joining with is finished. And that calling thread doesn't do anything while you've joined. There's also a similar method, join, on a fork join task, except fork join task doesn't simply block the calling thread. Instead, it uses the worker thread to run other tasks. And I call this the collaborative Jiffy Lube model of processing, or also called the let's pitch in and help out. So I'll try to explain this. Hopefully this will make sense. If you've never gone to Jiffy Lube, this may not make any sense. But I'll explain Jiffy Lube, and if you go to Jiffy Lube, it'll make more sense. So Jiffy Lube is a place where you go to get your oil changed. And so they offer fast, relatively inexpensive oil changes. And they're typically organized by having a shop with several bays. So you can see here we have 4 bays. And each bay is a place for a car to drive in to get its oil changed. And each bay typically has a couple of attendants, maybe 2 or 3, who will change the oil. But they also do other things. They'll check your tire pressure, they'll check your fluid level, they'll inspect your windshield wipers, they'll look at your filters. There's like a 12 to 20 step thing that they do. So it requires multiple people to do this most efficiently. So imagine in steady state, you've got all the cars in each of the bays. Each bay has a car, so you might have 4 cars. You might have, let's say, 2 attendants per bay. They're working away. But what happens when, some of the cars leave and there's nobody else to come in? Well, what you can do in that case is the people who work in one bay who don't have anything else to do could migrate over to the other bay and pitch in, right? They could say, oh, well, we'll check the oil filter while you change the oil. Or we'll check the air filter while you change the oil. We'll check the tire pressure. We'll check the temperature gauges. We'll test all these different things. So other workers at Jiffy Lube, other worker threads, can pitch in to do work when they don't have anything else to do. And that's the same way that ForkJoinTask.join works. So when that's called, the worker thread will, of course, wait for that task to finish. But if that task is off still computing in the background, the worker thread won't just wait. It'll go and run other tasks. This is all part of the work stealing stuff we talked about before. And when that worker thread finally encounters the subtasks for which it was joined, or for why it was called, then it'll say, okay, now I'm done. But up to that point, it'll keep processing things and running other tasks, pitching in, as it were. Okay, so that's a quick overview of the ForkJoin task. And now we're going to talk next about other elements of the ForkJoin pool.